Alright, so here's how a G protein works. Basically, you have your G protein right here, and that is loosely attached to the cytoplasmic side of the membrane and acts as an on-off switch for this enzyme. Now, when a signaling molecule, which is going to be this, is active, when a signaling molecule binds to the receptor is activated and changes shape, allowing this G protein over here and its GDP bound to it to bind to the G protein coupled receptor. Which, when it does bind now, just imagine that these two are connected together. It'll move, which it won't. Come on. There we go. And then its GDP, which is attached to it, bind to the coupled receptor. But this GDP right here is displaced by a GDP, which is basically another form of energy. Now, the activated G protein dissociates from the receptor and diffuses along the membrane and binds to an enzyme. So this is going to diffuse through the membrane. Now this GDP is still attached to it. I just couldn't, keep them attached. So through the membrane, do. All right, and everything is bound to this enzyme here now. Once activated, the enzyme can trigger the next step, leading to a cellular response. Now, binding of signaling molecules over here is reversible. They can bind and dissociate many times, making this reaction happen many, many times over, or stop completely. The changes in the shape of the enzyme are temporary because the G protein functions as a GTPase enzyme. So this enzyme then hydrolyzes the G protein that's bound to its bound GDP to GDP. So this is hydrolyzed, then you get some GDP out of that again. And also another product is inorganic phosphorus. And after that, this G protein comes back to what it was doing, sitting on the membrane with its GDP, and this inorganic phosphorus goes off and is useful somewhere, if it'll move. Come on. There. So yeah, G proteins are used in diseases like whooping cough. That disease specifically affects the G protein and its receptors. So yeah, G proteins. How does this stop? There we go.